Welcome dear students. In my previous video on this topic, moving charges and magnetism, I told you how a charged particle travels in a circular path when it is projected perpendicular to a uniform magnetic field. Today I will discuss the expression for the radius of the path taken by the charged particle, its time period and frequency of revolution. As I told you in the previous discussion that if I have a uniform magnetic field which is in this case directed perpendicular to the plane of the board inwards, a positive charge plus Q is projected perpendicular to this field, then it will experience a force F equal to Q into V into B sine theta. Since theta is 90 degrees, so sine theta is 1. Therefore, F is equal to Q into V into B will be the amount of force this charge will experience. The direction of the force experienced is given by Fleming's left hand rule, which causes this charged particle to move in a circular path. We will see that the time of revolution of the charged particle is fixed for a definite charge and a definite magnetic field. Let us first see the expression for the radius of the circle which the charged particle will move in when it is projected perpendicular to the magnetic field. You know that if any mass m is moving at a speed v in a circle of radius r, then it requires a centripetal force F equal to mv square upon r. So if the charged particle here has mass m and its velocity is v, then it will also require a force F equal to mv square upon r for its revolution in this circular track. This force will be supplied by the force which the magnetic field is exerting on it. So we can write Q into V into B is equal to mv square upon r. M is the mass of this charged particle. This leads to r equal to mv upon q into b. This is the radius of the circle in which the charged particle will move. You can see that the radius depends on the velocity of the particle if its mass and charge are not changed. Greater the velocity, greater will be the radius. Now we will see the expression for the time period of revolution of this charged particle in the circular path. You know that if t is the time period of revolution of the particle in the circular path, then in one time period it will travel a distance equal to the circumference of the circle, and that will be equal to 2 pi r. So using the equation speed equal to distance upon time, we can write time equal to distance upon speed, so that time period is equal to 2 pi r upon v. Replacing r by mv upon qb, we will get t equal to 2 pi mv upon v into qb. This gives us t equal to 2 pi m upon qb. From this expression you can see that the time of revolution or time period of revolution of the charged particle in the circle is independent of its velocity. That is, if the velocity increases or decreases, even then the charged particle which has charge q, mass m, will move with the same time period. This can be attributed to the fact that when the velocity increases, the radius also increases in the same proportion, so that the time taken by the charged particle to complete one revolution remains the same. From this expression, we can find out the frequency of revolution of the charged particle in the circle. We know that the frequency is the reciprocal of time period. So the frequency of revolution of this charged particle in the circular path will be 1 upon 2 pi into qb upon m. Just like time period is independent of the velocity of the particle, the frequency of revolution is also independent of its velocity. Unless we change the value of q, b or m, the frequency of revolution will not change. It will not depend upon the radius of the circle or the velocity of the charged particle. On this basis, we will study the charged particle accelerator known as cyclotron. For that, keep on watching and wait for my next video. Thank you.